Okay, so in this tutorial, we will talk about normal shocks. Okay, so what are normal shocks? A normal shock, okay, in a flow of a compressible fluid. Okay, we have some compressible fluid, for example, air. A normal shock is a thin region of dramatic pressure increase. Okay, that's just one of the conditions that change, but it's not just pressure. Okay, other things change, for example, density and temperature and so on. Okay, but yeah, so I'm simply going to describe to you that a normal shock is an infinitesimally thin region of sudden pressure increase. Okay, so why did they call it normal? Okay, it's not normal in the sense of it's normal and abnormal. Normal here means perpendicular. Okay, and why is it perpendicular? Because if the flow is moving like this in this straight line, then you see this shock is perpendicular to the flow direction, right? And remember, another word for perpendicular is normal. So that's why we say that we describe this shock to be a normal shock, because the plane in which the shock sits in is normal to the flow direction. Okay, so that's why they call it normal shock. Yeah, there are other types of shock which we are not covering in the syllabus. For example, oblique shock. Okay, oblique shock means the shock, right, is some angle uh away from the flow direction that is not 90 degrees. Okay, so that's what it means by oblique shock. Yeah, but we're not covering this kind. I'm just telling you the different kinds of shock. Yeah, so that's why they specify as normal shock. Okay, so how do you deal with normal shocks? Okay, I need to describe to you the structure of a normal shock. So what do I mean by the structure of a normal shock? So suppose we're given this example of a normal shock. So here we have a nozzle, okay, a varying area nozzle, and then we have fluid flowing to the right, and then there happens to be a shock somewhere inside this nozzle. Okay, so what is the important parts of a nozzle? So here, a shock, we consider it to be infinitesimally thin. So let me write that down. Infinitesimally thin. Okay, so we consider the shock node infinitesimally thin. So what do I mean? I mean, you see this width of the shock, I mean the thickness of the shock, this thickness, we consider it to be infinitesimally thin. That means it's so thin, right? We consider it almost to be zero. Yeah. So how big is this? We consider it to be almost zero dimension. Okay. So it's so thin that for all intents and purposes, it's almost zero thickness. Okay. Now, what other parts are there in a shock? In a shock, right? We label two important points. Here, the one before the shock, and here, the one after the shock. So usually we label them as points 1 and points 2. Okay, but then you can also label them as points 2 and points 3 accordingly. Okay, assuming like, for example, you have already a point labeled 1 here, then there'll be 1, 2, 3. Okay, so this 1 is the upstream, is the point upstream of the shock, and this point number 2 is a point downstream of the shock. Okay, upstream means, okay, so if this is the flow direction, upstream means this way, okay, to the left, and then downstream means along the flow direction, so downstream. Okay, so this is what it means by upstream and downstream if this is the flow direction. Okay, so point 1 refers to the point upstream, just upstream of the shock, and point 2 refers to the point that is just downstream of the shock. And remember how I said that this is infinitesimally thin, right? But why do we, draw them as two separate points, well, it's just an exaggeration. Okay, we just exaggerate the thickness of the shock so that they do not overlap, right? Because technically speaking, if it is so thin, right, then they would points 1 and 2 would exactly overlap. But yeah, we exaggerate it just to be clear. So upstream of the shock, there is a set of conditions, okay? So it's temperature, pressure, and speed. And then downstream of the shock, there is its own temperature, pressure, and velocity, okay? And it's usually the case that pressure 2 is greater than pressure 1, okay? What else is there? What else is important to know about the structure of a shock? Okay, the structure of a shock, right? Okay, assuming the flow direction is to the right as shown in this diagram, assuming that the flow direction is in this direction, okay, the point upstream of the shock is always supersonic, whereas the point downstream of the shock is always subsonic. Okay, this is important to remember. Okay, so when you're given a shock and the flow direction is this way, it is always supersonic here, and then right after the shock, it will be subsonic. This is important to know. Why is it important to know? Because sometimes you're put in a position to solve for the Mach number at these 2 points. And if you calculate that, the Mach number here is less than 1, then you know you are wrong. Okay? You must go for the option where the Mach number is greater than 1, because here is supersonic. And here, you must make sure that your Mach number is less than 1, otherwise you know that you're wrong. Okay? So this is important to know the general structure of a shock. That is to say, along the flow direction, upstream of the shock must be supersonic, downstream of the shock must be subsonic. Okay, this is an important fact that you have to remember. Okay, so now let's look at the basic equations of a shock. So I'm sure you already know the continuity equation, okay, mass conservation. This is easy enough to know. So in the momentum conservation, which is basically the force balance equation, because the shock is so thin, the reaction force is considered to be 0. Okay. So I'm not gonna delve deep into this because we don't use this much. What's interesting is more so the following equation. So this one. What is this? So I know the lectures serve it to you in this way, but let me rewrite it in a different way that is easier to understand. Okay. So we have a shock, right? And then we have the points 1 and 2. This is the flow direction. For any 2 points, okay, actually, it doesn't have to be shock. If you have a flow, right? Okay, this is a flow. If you have points 1 and 2, okay, for any 2 points, the moving fluid has its associated energy. Okay, it has its associated energy. In general, right, the energy at any point is given by this expression, h plus v squared over 2. Okay, so if we're considering the energy at point 1, then it will be h1 v1 squared over 2. If we're considering the energy at point 2, then it'll be h2 plus v2 squared over 2. Okay, and likewise, if it's 3, then it'll be h3 v3 squared over 2. Okay, so what is this expression showing? Okay, one part of the expression is the enthalpy. Okay, and another part of the expression, okay, loosely speaking, this shows the kinetic energy. Okay, so my explanations here are going to be loose. They're not going to be strictly scientific, but I hope it still gets across the ideas of energy in a moving fluid. So enthalpy is a defined term which comprises of the internal energy and the flow work of the fluid. Okay, so this contains the internal energy and the flow work of the fluid. You don't really have to know what those details are, but I'm just telling you that, okay, at the end of the day, what you need to know is enthalpy is just part of the energy of a flowing fluid. The other part of the energy of the flowing fluid is the kinetic energy. Okay, so these are the two main parts of uh the energy in a flowing fluid. Okay, now why is that important? Consider the case where you inject some energy into the fluid flow between 1 and 2. Okay, so you are injecting energy into here. Usually this is thermal energy. So you're injecting heat into the fluid flow between 1 and 2. Okay, so to be more precise, right, we don't just say energy, we denote it as dq dm. Okay, so this is the energy per unit mass. Okay, so for each unit of mass, so meaning to say, for example, for each kilogram of fluid, we inject some energy. Okay, so that's what it means by energy per unit mass. For a unit mass, so for example, a kilogram of fluid, we inject some energy, okay, into the flow. Now, because we inject energy into the flow, the energy at the energy at 2 is different from the energy at 1, right? So in this case, since we're injecting energy, the energy at 2 is higher than the energy at 1. Okay, so we can say that, okay, H2 plus V2 squared over 2, this is the total energy at 2 minus H1 plus V1 squared over 2 is equals to dq df. So let me help you make sense of this. This is energy. So let me use a different color. This is energy, the total energy at 2, and this is total energy at 1, which is equal to the energy provided. Right? So the difference between energy at 2 and energy at 1 is given by the energy that we injected into the fluid flow. Okay, so I hope this qualitatively makes sense to you. Okay, now what's different about a normal shock? You see, a normal shock, right? Remember, we consider it to be infinitesimally thin, so it's super thin, right? What is so important about it being thin is the fact that if it is so super thin, then we can consider that in this control volume, okay, so now we are considering this control volume that just captures the shock. Because it is so infinitesimally thin, we consider the fact that no heat is being able to transfer into the shock, right? Because if this is 0 dimension, right? If this is 0 area, then there's no area for heat to flow into the shock, okay? So at the end of the day, we can consider the shock to be adiabatic. Okay? Meaning to say, no heat is being able to transfer into the shock control volume. Okay, so we consider that no energy can be transferred in the form of heat into the shock. Okay, so what does that mean? Essentially, this means here that for a shock, right, specifically for a shock, this will be 0. Okay, because it is infinitesimally thin, heat cannot be transferred into the shock, therefore dq dm is equal to 0. Now, why is this important? This is important because we can make a trick. Okay, we can make a trick, or we can make a hack. Okay, so what am I referring to? I'm going to refer to this hack here. You see, this shows the TS diagram for a shock. Okay, so right here, we have a shock occurring. Then there's some changes in the condition. So you see, temperature and pressure has changed from T1 P1 to T2 P2 respectively. Okay, but take a look at the stagnation conditions. The stagnation conditions state that while the stagnation pressure might be different, the stagnation temperature are the same. Okay, point 1 and point 2, even though a shock has occurred, they both share the same stagnation temperature. Okay, a shock, right? The point upstream of the shock and the point downstream of the shock, for some reason, they share the same stagnation temperature. And let me prove to you why with the discussion we have here. So remember, it is adiabatic, a shock is adiabatic, so we consider no energy transfer. Now, what is the definition of a stagnation point? Stagnation means velocity equals to 0, okay? So now we want to see the difference in energy of the stagnation point. Okay. So okay. Let me draw a flow. This is point one, this is point two. Okay. And then this is the stagnation point of one and the stagnation point of two. Okay. So in order to get from one to 0, 1, okay, 1 to its stagnation point, this is a isentropic process. Okay. You isentropically decelerate it into 0 velocity, right? Because you isentropically did it, there's no energy loss or gain, okay, because it's reversible. Therefore, the energy at 1 is equal to the energy at 2. Sorry, let me say that again. The energy at 1 is equal to the energy at 0, 1. Okay, so the energy at point 1 is equal to the energy at its stagnation state. Likewise, because you isentropically bring 2 to 0, 2, okay, there's no energy change. Therefore, therefore the energy at 2 is equals to the energy at its corresponding stagnation point. Okay, so therefore you can equate this to the energy at its stagnation point. So this would be HO2 plus VO2 minus HO1 plus VO1 squared 2. Okay, so this is equals to 0. Now, what else? You know that by definition, stagnation point means 0 velocity, right? So at the stagnation points, so at this point and this point, the velocity of the fluid is 0. Therefore, we can just drop this term because this is 0 and this is 0 since they are the stagnation points. And what we're left is this HO2 minus HO1. So this is the enthalpy change between the stagnation points. Okay, so you remember to find enthalpy change, right? You use the formula Cp T02 minus T01. How do I get this? It's because I know that enthalpy change is given by the formula Cp delta T. Okay, so this is an old formula that we have already been familiar with since thermal fluids. Yeah, so I'm applying that formula, and to find the enthalpy change, I just apply that formula. So the delta in H, so the change in enthalpy is given by Cp times the change in temperature. Okay, so you can move Cp the other side, and then you're left with T02 minus T01. And then if you bring T01 to the other side, you will end up with T02 is equal to T01. So see, we've proven that for an adiabatic process, okay, for a shock, T02 is equal to T01. The stagnation temperatures of the point upstream and downstream of shock are equal. Okay, they share the same stagnation point. And it's not just shocks only. Okay, it's not just shocks. This property is not exclusive to shocks. This property will hold as long as the process is adiabatic. Okay, so as long as it's adiabatic, the flow is adiabatic, the 2 points will share the same stagnation temperature. This is important because we will use this trick, especially when we find entropy change for an adiabatic flow. So let me write that down because this is very important. Okay, for for adiabatic flow, any 2 points on the flow will share the same stagnation temperature. Okay, so let me read this here. So this is an important thing that you have to remember throughout your compressible flows. Okay, so for an adiabatic flow, any 2 points on the flow will share the same stagnation temperature, and it's only temperature. It's not any other conditions. It cannot be pressure. It cannot be density. It is only stagnation temperature for an adiabatic flow. Okay, wait, yeah. So you have a flowing fluid, and we consider this to be adiabatic. So no heat transfer occurs. Then we have point 1 here and point 2 here. Okay, since it is adiabatic, okay, you do not have to derive this, but I'm just showing you that as a consequence of it being adiabatic, the stagnation temperatures are equal. Okay, so we have point 1 and point 2, right? If the flow is adiabatic, then you can automatically say that the stagnation temperatures are equal. Okay, this is an important fact that you must remember. Okay, so it's not just for shocks. There are other flows which are adiabatic too. For example, isentropic flow, right, is considered adiabatic because isentropic means that you are reversible and adiabatic. And you already know for a fact that uh, isentropic flow share same stagnation conditions. Okay, and you see one of the stagnation conditions is the stagnation temperature. So you see it satisfies. Okay, so it's not just shocks only. In the future, we will see other flows which are also adiabatic. So this you better keep in mind. Okay, so what else is important in this list of equations? So shocks are irreversible, meaning to say there'll be entropy change. Okay, so in fact there'll be entropy increase. Okay, across a shock. So point 2 will lead to an increase in entropy compared to point 1. Okay, equation of state we're familiar with. Entropy change, which is already talked about. And in order to find that entropy change, you calculate it using the Gibbs equation. So mostly we'll be using this version of the Gibbs equation. Even though there are multiple variants of the Gibbs equation, I'll be mostly using this specific variant. Okay? Yeah. So yeah, this diagram shows the stagnation temperature being equal. So remember, it's only stagnation temperature. You see, only stagnation temperature is being shared, whereas you see, P01 is not equal to P02. So not all stagnation conditions are shared. For a shock, it is only the stagnation temperature. Okay? Okay. Should move on. Hold on. Okay. Yeah. So what about this diagram? Well, this diagram shows what happens for a converging diverging nozzle as you vary the back pressure. So let me illustrate what I mean. So here we have converging diverging nozzle where the inlet is connected to a large tank. So at a large tank, we can consider the conditions to be stagnation conditions. Okay, this doesn't change. Okay, so this is fixed. But what can be changed is the back pressure. This is what we control. Okay, so we can control this using a control panel, and we'll be controlling the back pressure. Okay, so this diagram is the result, but I'm going to show you step by step how do we obtain this. So here we have pressure axis and the x-axis. The x-axis just shows the location in the nozzle, right? So if this is the nozzle, right, then x is simply the location. So this is one x location, this is another x location, this is another x location, this x location is for the throat, and so on. Okay, so this is pressure. Okay, so this is P, yeah, the pressure at the back here. Okay, and then over here, there's another vertical axis, and this is the back pressure. So this is PB. Over here is PB. Yeah, and then here is P naught. So throughout this whole process, right, we're gonna keep P naught the same. The only thing we're gonna change is PB, and specifically, we're going to lower PB, because when both of them are the same, right, no flow occurs. Okay. Now we're going to move PB downwards a bit. So when we move it down, then some flow will start to occur. So you have this. So how will the pressure vary along the nozzle? Okay, so how it varies is it will dip down, reach a minimum at the choke, and then climb back up towards the back pressure. Okay, now let's move the back pressure down again. Okay, again it will dip down, reach a minimum at the choke, and then climb back to the back pressure. Okay, it's important to note that this whole thing is subsonic. Okay, all of this is subsonic for now. Okay, now what happens when at a certain point? So at a certain point, right? Okay, when we further decrease the back pressure, there will be a back pressure such that the choke will finally reach Mach number equals to 1. So let me label here with an arrow. This will be a point where Mach number equals 1. Yeah, so you can decrease the back pressure, and there will, if you keep decreasing it, there will be a point where the choke will finally reach a Mach number equal to 1. Okay, keep in mind that the first two lines, right, throughout is just subsonic. So throughout is just Mach number below 1. However, there is a certain back pressure to which when you decrease this towards this back pressure, the choke will eventually reach a critical condition, meaning to say Mach number equals to 1. If you lower the back pressure any lower than this line, what will happen? Okay. What happens is, oh sorry, don't know why it becomes a straight line. What happens is, finally, the just behind the choke, okay, so this is the choke location. Just behind the choke, there will be supersonic flow. Okay, and the supersonic flow is usually accompanied by shock. Okay, so that wiggly line over there is the shock. So let's look at this specific line that I just draw and describe to you the Mach number regions. So before the choke, this was entirely subsonic. This is subsonic. Then here, just after the choke and before the shock. So between the shock and the subsonic region, this will be supersonic flow. Okay, this will be supersonic flow because the diverging nozzle will cause a supersonic acceleration. Okay, and of course, like I said, this vertical line here is actually a vertical squiggly line like that. Is a shock. So as you can see, the shock, right? Remember that the vertical axis represents pressure. So you see, the shock causes a sudden increase in pressure. So your pressure suddenly jumps from here to here. Okay? And then after the shock, this will again be subsonic. Okay? So in this situation, right, the shock will be somewhere like that. Okay? Yeah. So that's how a shock normally looks like. And then if you lower the back pressure any lower, right, your shock will simply move towards the right in this arrangement. So it will, again, keep going down, and then the shock will occur somewhere here, and then it will return to the back pressure. So yeah, again, this will be subsonic, followed by supersonic, followed by the shock, and then followed by, again, a subsonic region. Okay? Yeah, so this is what happens when you lower the back pressure for a converging diverging nozzle. Okay, somewhere once once the diverging section reaches supersonic, there is a chance that it will have a shock because finally the fluid is moving supersonic, right? So always it takes supersonic fluid to create a shock, right? It always takes a supersonic flow to create a shock. Okay, yeah. So that's this diagram covered. Okay. Now, what about this diagram? This diagram, right, is important because it teaches you which set of tables to use for which part of the flow. Okay, so here we have a converging diverging nozzle, which has a shock over here, right? Besides the shock, the other points are all uh, isentropic. So from 0 to 1, this is an isentropic flow. Then from 2 to the exit, this is also an isentropic flow. But they're not the same isentropic flow. They are two separate isentropic flows. So that's why I'm going to call this isentropic flow A and isentropic flow B. Okay, they are two different isentropic flow. And how are they different? They're different because they have different reference states. Okay, in other words, they have different stagnation points and different critical states. Okay, so the stagnation point of this flow is not the same as the stagnation point of this flow. They're not equal. Okay, yeah, and between these two isentropic flows, so here is the shock. Okay, so what is my point when I show you this flow? My point is that within this region, you will use the isentropic flow function or the isentropic flow tables. Same here, between 2 to E, you will also use the isentropic flow function or the isentropic flow table. However, between 1 to 2, if you want to find any properties, then here you have to use the shock tables or the shock flow functions. Okay, and this is important when you go through the tutorials. Yeah, this is how you find the various conditions in the flow containing a shock. You must identify, okay, between this point and this point, is it an isentropic flow or is it a shock? So I will use the appropriate table. Then between this point and this point, is this an isentropic flow or is it a shock? Then I will use the appropriate table. Okay, so that's why it's important to know this much. Okay, so yeah, I covered much of the lectures related to shock. I'll see you in the next video for the tutorials.